Hi friends, in this video we are going to see the JEE Main previous year questions in the topic D block elements. In my previous video, I have explained the key concepts of D block elements. Please go and watch that video so that it will be easy for you to solve the questions. Let's get started. The first question is from April 9, 2024. The electronic configuration of Cu2 ion is 3d9, whereas that of Cu1 is 3d10. Which of the following is correct? Cu2 is less stable. Stability of Cu1 and Cu2 depends on nature of copper salts. Cu2 is more stable. Cu1 and Cu2 are equally stable. So we can see the electronic configuration. Cu1, that is copper in +1 oxidation state, is having fully filled d orbital. We may consider this as more stable configuration, and we can say that Cu1 ion is the most stable ion. But if you see the Cu2 ion in solution is more stable because it releases more hydration enthalpy. This hydration enthalpy is very much greater that it compensates the second ionization energy. So whenever Cu1 ion, or we can also write as Cu plus ion, is present in the aqueous solution, it readily loses one electron and it becomes Cu2 plus ion, because the energy required for the removal of the second electron, that is the second ionization energy, is compensated by the more negative hydration enthalpy. So Cu plus readily loses one electron and it forms the more stable Cu2 plus ion. How this Cu2 plus ion is more stable? Because it has high charge density. That is, the size of Cu2 plus ion is very small and it has high nuclear charge. So it has high charge density and it forms stronger bonds with water molecule. So for this reason, Cu2 plus ion is more stable than the Cu1 ion. So the correct answer is option C. Let's go to the next question. There are two statements. The first statement is higher oxidation states are more stable down the group among the transition elements, unlike p block elements. So we know p block elements. For p block elements, let us take for example group 14 elements: carbon, silicon, germanium, tin, lead. So for these elements, when we are going down the group, the higher oxidation states are less stable. So for carbon, +4 oxidation state is more stable. For silicon also, +4 oxidation state is more stable. But as we go down the group, for lead, +2 oxidation state is more stable. This is because of inert pair effect. So this you might have studied in p block elements. But if we go to the d block elements, that is the transition elements, for the 3D series, when you compare that with the 4D series and 5D series, 4D series and 5D series have stable compounds in higher oxidation states. This is because the 4D orbital and 5D orbital are very large and diffused and they are spread out in space. So they easily form strong bonds with the ligands, and also as we go down the group in the d block elements, down the group, the effective nuclear charge increases. So the effective nuclear charge is going to stabilize the metal in the higher oxidation state. So for these reasons, the higher oxidation states are more stable down the group. Down the group here they are referring to 4D and 5D series, unlike the p block elements. So the statement 1 is correct. Now we'll go to the second statement. Copper cannot liberate hydrogen from weak acids. So this statement is also true because I already explained in that video in which I explained the key concepts. Copper is having the electrode potential value of the M2 plus bar M, that is Cu2 plus bar Cu, value of plus 0.34 volt, which is greater than hydrogen. We know that the electrode potential value of hydrogen is 0. So as the copper atom is having the electrode potential value greater than hydrogen, it cannot displace H2 gas from the weak acids, and we also know that copper lies below the hydrogen atom in the reactivity series. So copper cannot liberate hydrogen from weak acids. So the statement 2 is also correct. So the correct option is option C. Both statement 1 and 2 are true. Go to the next question. A transition metal M among scandium, titanium, vanadium, chromium, manganese and iron has the highest second ionization enthalpy. So for this you have to know the electronic configuration of the given elements. Then after the removal of the one electron, what is the change in electronic configuration? You have to compare that. So let us see that. For scandium, the electronic configuration is core argon configuration 3d1 4s2. After the removal of one electron, it becomes argon configuration is already there 3d1 4s1. So this is for scandium. Then you will go to titanium, 3d2, 4s2. Titanium, after the removal of 1 electron, 3d2, 4s1. Vanadium, 3d3, 4s2. Vanadium, after the removal of 1 electron, 3d3, 4s1. Then going to chromium, the general electronic configuration is 3d5, 4s1. Then after the removal of the first electron, it becomes 3d5, 4s0. Then for manganese, 3d5, 4s2. Manganese in +1 oxidation state is 3d5, 4s1. Then for iron, 3d6, 4s2. Iron in +1 oxidation state, 3d6, 4s1. So now you have to see the electronic configuration of these elements in their +1 oxidation state, and you have to check for which ion there is a stable configuration. So from that ion, if you take the next electron, that is the second electron, if you take that, it will require more amount of energy. So let us see that for scandium in +1 oxidation state, there is no stable configuration and all. Then for titanium, vanadium ion also, in their +1 oxidation state, there is no stable configuration. For chromium in +1 oxidation state, the configuration is 3d5. 3d5, you already know that it is half-filled configuration. So for the removal of the second electron from this half-filled configuration, more amount of energy is required. So Cr plus is going to have the highest second ionization energy. So in this question, what they are asking, the transition metal M among the given elements has the second highest second ionization enthalpy. So chromium is having the highest second ionization enthalpy. The spin-only magnetic moment value of M plus ion. So now you have to find the spin-only magnetic moment value of M plus means Cr plus. For that, you have to know the number of electrons. Number of electrons, we have already written the electronic configuration. So the electronic configuration is 3d5, and you have to know the number of unpaired electrons. So from the configuration, we can clearly see that the number of unpaired electrons n equal to 5. Now they are asking the spin-only magnetic moment. The spin-only magnetic moment formula mu is equal to root of n into n plus 2. N value we have found as 5. So root of 5 into 5 plus 2 is 7. So root of 35, which will come as 5.92 bm Bohr magneton. Then they are asking the near integer. So we can round off this to 6 bm. So the answer is 6. Let's go to the next question. Ion 3, that is Fe3 plus, catalyzes the reaction between iodide and persulfate ions. So you have to know that Fe3 plus gains 1 electron and it is reduced to Fe2 plus. So this is the reaction, and they are telling it is acting as a catalyst. So again, what will happen? This Fe2 plus again loses 1 electron and it will again become Fe3 plus. So when this Fe3 plus is gaining 1 electron and it is getting reduced, so at this time, this Fe3 plus will act as oxidizing agent, and this Fe2 plus loses 1 electron. So at this time, it is getting oxidized, but it will act as a reducing agent. The meaning is, when a substance is getting reduced, it will oxidize the other substance which is present in that reaction, and when a substance is getting oxidized, it will reduce the other substance which is present in the reaction. So in this case, iodide ion is given. Iodide is I minus. So iodide ion will be converted to iodine molecule. So you keep that in mind. Then persulfate ion is given, that is S2O8 2 minus. So we will see the reaction. So the reaction is first Fe3 plus, that is only given question. So that is going to react with the I minus iodide ion. Then Fe3 plus is converted to Fe2 plus by the addition of electron, and that electron is given by this iodide ion. So this iodide will be converted to iodine molecule. So how can we check that, confirm that? Iodide ion is having the oxidation state of -1. I2 is a molecule, neutral molecule, and that will have the oxidation state of 0. So from -1 to 0, it is increase in oxidation number, and the increase in oxidation number is oxidation. So we can say that Fe3 plus ion oxidizes this I minus ion. So you have to see the option. So in option A itself, they have given Fe3 plus oxidizes the iodide ion. So that is correct. Then we will go to the next equation. Now Fe2 plus is there in solution. So that one is going to react with persulfate ion, S2O8 2 minus. So now this Fe2 plus again loses 1 electron and it will be converted to Fe3 plus Now this S2O8 2 minus will be converted to SO4 2 minus ion. So how to check that? You have to find the oxidation number of sulfur in this compound. So let us check that. So I will underline the element sulfur. 2 sulfur atoms are there. So 2x plus, for oxygen atom the oxidation number is -2 and 8 atoms are there. So everything equal to the charge of this ion is -2. So 2x minus 16 equal to -2, 2x equal to 14. So x is equal to +7. So for one sulfur atom the charge is +7. Now going to the next molecule, x sulfur plus, for one oxygen atom -2 into 4 oxygen atoms are there, then everything equal to -2. So x minus 8 equal to -2, x equal to +6. So here sulfur is having the oxidation number +6. So here from +7 it has changed to +6. So decrease in oxidation number is reduction. So here Fe2 plus reduces S2O8 2 minus. So here Fe2 plus reduces the persulfate ion. D option is correct. Then now if you see the two equations, these are not balanced. So you have to balance the equation also. So see the first equation, 2 iodine atoms are there in the product side. So here just write 2. So as each iodide ion is going to give electron, so 2 moles of this Fe3 plus ions will be reduced to give 2 moles of Fe2 plus ions. So in this solution also 2 moles of Fe2 plus ions are there. And then if you see the second equation, 2 sulfur atoms and 8 oxygen atoms are present in the reactant side. So just we are going to write 2 in the product side, 2 SO4 2 minus ions. So here the correct options are A and D. So the correct option in the given question is option D, A and D only. The next question is the spin only magnetic moment value of MO4 2 minus, where M is a metal having least metallic radii among scandium, titanium, vanadium, chromium, manganese and zinc. So I have already explained in that key concepts itself that chromium is the metal which is having the least atomic radii, or you can say least metallic radii. So here the metal M is chromium and it is in the formula CrO4 2 minus. So they are asking us to find the spin only magnetic moment value for the metal. For that you have to know the charge of the metal, then you have to count the number of unpaired electrons. So let us find the charge of the metal. So let us keep chromium as X, and we know that the oxidation state of oxygen is -2 and 4 oxygen atoms are there, equal to the overall charge is -2. So X minus 8 equal to -2, X equal to +6. So what is the configuration of chromium? Core argon configuration 3d5 4s1. Totally 6 electrons are there and chromium in +6 oxidation state. So all the electrons are lost. So 3d0 configuration. So there is no unpaired electrons. So n equal to 0, and the formula of spin only magnetic moment mu is equal to root of n into n plus 2. So here n value is 0. So mu equal to 0. So 0 is the answer. The next question is arrange the following elements in the increasing order of number of unpaired electrons. So you have to know the electronic configuration of these elements. So the first one is scandium, which is having the electronic configuration 4 argon configuration 3d1 4s2. Then you are having chromium 3d5 4s1. So from this configuration itself it is clear that in d orbital itself 5 unpaired electrons are there, and in 4s orbital also there is 1 unpaired electron. So both in 3d and 4s orbital unpaired electrons are there. So you have to count everything, and the number of unpaired electrons in chromium is 6. So for scandium, how many unpaired electrons are there? In 4s orbital 2 electrons are there. So both the electrons are paired. So only in 3d orbital you are having 1 electron. So the number of unpaired electron is 1. Then the next element is vanadium. So the configuration is 3d3 4s2. So the number of unpaired electron you have to count only from the 3d orbital 3. Then for titanium 3d2 4s2. So the number of unpaired electron is 2. Then manganese 3d5 4s2. 4s orbital is fully filled. So the number of unpaired electron from 3d orbital is 5. So let us write the options A, B, C, D and E. So now we are going to write in the increasing order of their unpaired electrons. So the least is scandium, A. So A is the least. Then after scandium you are having titanium, which is having 2 unpaired electrons. So after A you are having D. Then after D you are having C, vanadium. Then after C you are having E. Then you are having B. So the correct option is option D. So this is the increasing order of the unpaired electrons. among VO2 plus MnO4 minus Cr2O72 minus the spin only magnetic moment value of the species with the least oxidizing ability. So first you have to know the charge of the metal. So in first compound you have to see the charge of vanadium, then manganese, then chromium. So in VO2 plus, so let us see the charge. For vanadium you have to keep it as X. Then we know that for oxygen -2 is the oxidation state. 2 atoms are there. So -4 equal to +1. So this -4 goes to the right hand side and it will become +5. Vanadium is having the configuration 3D3 4s2. Now vanadium in +5 oxidation state, all the 5 electrons are lost. So 3D0 is the configuration. Then going to MnO4 minus X, and 4 oxygen atoms are there. For 1 oxygen atom, the oxidation state is -2. So -2 into 4 is -8 equal to -1. So when -8 goes to the right hand side, it will become +8, and already -1 is there. So it will become +7. So the configuration of manganese is 3D5 4s2. Now all the 7 electrons are lost. So Mn plus 7. 3D0 is the configuration. Then going to the next one, Cr2O72 minus. So 2 chromium atoms are there. So 2x. Then you are having -2 into 7 is -14 equal to -2. So 2x is equal to +12. X is equal to +6. The configuration of chromium is 3D5 4s1. All the 6 electrons are lost in +6 oxidation state. So here also the configuration is 3D0. So all the 3 ions are having 3D0 configuration. Now here the condition given is least oxidizing ability. So here you have to know the point that oxidizing ability is directly proportional to the oxidation state. Here you have to know the point that oxidizing ability is directly proportional to oxidation state. That is, higher the oxidation state of the ion, higher will be the oxidizing ability. That is, the element should oxidize the other substance and itself it should be reduced. So what is meant by reduction? That is, easily gains electrons. So now we are going to compare all these ions. Vanadium in +5 oxidation state, manganese in +7 oxidation state, then chromium in +6 oxidation state. So higher the oxidation state, easily it gains electrons and easily it acts as oxidizing agent. Now Mn +7 and Mn +6 both have higher oxidation state. So these two can act as oxidizing agent. So they have the oxidizing ability. But vanadium is in +5 oxidation state. So it has comparatively least oxidizing ability. So they are telling the least oxidizing ability which a species is having. So this VO2 plus is having the least oxidizing ability. Now what we have to find is the spin only magnetic moment value of the species. So for finding the spin only magnetic moment value, you have to know the number of unpaired electrons. Here you are having 0 electrons. So the number of unpaired electrons n equal to 0. So the spin only magnetic moment is mu is equal to n into n plus 2. So the value is 0. So the answer is 0. The next question is the spin only magnetic moment value of the ion among Ti2 plus, V2 plus, CO3 plus and Cr2 plus that act as strong oxidizing agent in aqueous solution is. So in the previous question itself we saw that the oxidizing ability is directly proportional to the oxidation state. That is, higher the oxidation state of metal, the more easily it gains electron. So it easily gains electron and it is itself reduced. So the ion is itself reduced and it is going to oxidize the other substance present in that reaction. So among the given ions, Ti2 plus, V2 plus, CO3 plus and Cr2 plus. So in these ions itself, clearly we can see that the higher oxidation state is CO3 plus. So CO3 plus will act as a strong oxidizing agent. Now they are asking us, to find the spin only magnetic moment value. So for CO3 plus, what is the number of unpaired electrons? So for CO, the electronic configuration is 3d7 4s2. Then for CO3 plus, 3 electrons are lost. So 2 electrons from s orbital and 1 electron from the d orbital. So it leads to 3d6 configuration. Now you have to count the number of unpaired electrons. So 1, 2, 3, 4, 5, 6. So totally you are having 4 unpaired electrons, n equal to 4. Now the spin only magnetic moment value mu is equal to root of n into n plus 2, which is equal to root of 4 into 4 plus 2. So root of 4 into 6, which is equal to root of 24. So the answer comes out as 4.89 bm Bohr magneton. But here they are asking the near integer. So we can round off this value to 5 bm. So the answer is 5. The next question is the metal that shows highest and the maximum number of oxidation state is. So we already saw in that key concepts itself. In 3D series, the element that shows maximum number of oxidation state is manganese. Manganese exhibit oxidation states from +2 to +7. And if we see the highest oxidation states for the given elements, for iron, it exhibits +6 oxidation state as the highest oxidation state. Then for titanium and cobalt, it is +4 oxidation state. That is their highest oxidation state. So for manganese only, you are getting +7 as the highest oxidation state. So the correct option is option B. Option B, manganese only shows highest and maximum number of oxidation numbers also. Let's go to the next question. In a borax bead test under hot condition, a metal salt is heated at point B of the flame. It results in green color salt bead. So the given elements are copper, nickel, manganese and iron. So these elements are heated at point B of the flame. The point A is called as the oxidizing flame and the point B is called as the reducing flame. Now they are telling that the elements are shown in the reducing flame. So you have to know what is the color given by these elements in the reducing flame. So the first element, copper, is colorless in the reducing flame. Nickel is giving gray color in the reducing flame. Manganese is also colorless in reducing flame, and iron gives green color in that reducing flame. Now they are asking us to find the spin only magnetic moment. So this iron which is giving the green color is present as Fe3 plus ion. So we have to find the spin only magnetic moment. For that you have to know the number of electrons present in that configuration. So you have to know the number of unpaired electrons. So iron is having the configuration, core argon configuration 3d6 4s2. So Fe3 plus, by the loss of 3 electrons, it becomes 3d5 configuration. So in 3d5 configuration, you know that the number of unpaired electrons is n equal to 5. So the spin only magnetic moment formula is mu equal to root of n into n plus 2. So root of 5 into 5 plus 2 is 7. So we already saw this. The answer will come as 5.92. So the near integer is 6. So the answer is 6 bm. The next question is the number of ions from the following that have the ability to liberate hydrogen from a dilute acid is. So the ions given are titanium in +2 oxidation state, chromium in +2 oxidation state and B2+. So out of these ions, to liberate the hydrogen gas from dilute acid, the condition is it should have the electrode potential value, that is the M2+ bar M. Standard electrode potential value must be negative. So if the standard electrode potential value is negative, then it can liberate hydrogen from dilute acid. So the given ions are from 3D series. We already saw in that key concept. Only copper will have positive electrode potential value. So the electrode potential value of copper is plus 0.34 volt. So out of all the 3D series, copper alone has positive electrode potential value. So what is the meaning? Copper alone cannot liberate hydrogen from dilute acid. But the given ions, there is no copper ion given. So all the 3 ions will have negative electrode potential value. So all the 3 ions can liberate hydrogen from the dilute acid. So the number of ions is 3. The element which shows only one oxidation state other than its elemental form. So the given elements are cobalt, scandium, titanium, nickel. So these elements belong to 3D series. We already saw in that key concepts video. In 3D series, 2 elements, scandium and zinc, exist only in one oxidation state. So you can tell that scandium and zinc exist in their elemental form, and other than their elemental form, they show only one oxidation state. Scandium exhibits +3 oxidation state and zinc exhibits +2 oxidation state. So these 2 elements do not exhibit any other oxidation state. They exhibit only +3 for scandium and +2 for zinc. So out of the options given, zinc is not mentioned here. So cobalt, scandium, titanium, nickel, scandium is the answer. So scandium always exists in only one oxidation state, +3 oxidation state, other than its elemental form. The next question is, a first row transition metal in its +2 oxidation state has a spin-only magnetic moment value of 3.86 bm. So here they are asking the atomic number of the metal is. So they are telling a metal in +2 oxidation state. So it has a magnetic moment value of 3.86 bm. So from the magnetic moment, we can calculate the number of unpaired electrons, 3.86, so which is near to 4 bm. So the number of unpaired electron is the value of the magnetic moment minus 1. So the number of unpaired electrons is 3. So this metal in +2 oxidation state has 3 unpaired electrons in its 3d orbital. So it exists in +2 oxidation state means the 4s orbital is not having any electron. So the metal ion will be having the configuration, that is the metal in elemental form will be having the configuration 3d3 4s2. So after the loss of 2 electrons only it will become m2 plus. So in its elemental form 3d3 4s2. So the the element which is having this configuration is vanadium, and the atomic number of vanadium is 23. So the correct option is option D. A first row transition metal with the highest enthalpy of atomization. So we saw that in 3D series, vanadium is having the highest enthalpy of atomization. So the value is 515 kilojoule per mole. So the first row transition metal they have mentioned here, so that metal is vanadium. Upon reaction with the oxygen at high temperature, forms oxides of formula M2ON. N value is 345. So they are telling that vanadium is reacting with the oxygen and it forms 3 types of oxides. So the N value is 345. So the first oxide is V2O3, next is V2O4, then the last is V2O5. So among these oxides, the spin only magnetic moment of the amphoteric oxide. So among these oxides, V2O5 is the amphoteric oxide. Now we have to find the spin only magnetic moment. So for finding the spin only magnetic moment value, you have to know the number of unpaired electrons. To know the number of unpaired electrons, you have to know the charge of the metal. So let us see this compound V2O5, and you have to find the oxidation state of vanadium. So 2 atoms are there, 2H. For oxygen, the oxidation state is -2, 5 atoms are there, so -10, and the overall compound is neutral, so equal to 0. So 2x equal to 10 and x is equal to +5. So vanadium is having the electronic configuration 3d3 4s2. 5 electrons are there, valence electrons are there, and vanadium in +5 oxidation state, which we got by calculation, has 3d0 configuration, that is there is no unpaired electron. So the number of unpaired electron is 0, and you know the spin only magnetic moment formula mu equal to root of n into n plus 2. So the answer is 0. So here the answer is 0. The transition metal having highest third ionization enthalpy. So let us see the option. Manganese is having the electronic configuration, core argon configuration 3d5 4s2. So after the removal of 2 electrons, it will become Mn2 plus. So it will have 3d5 configuration. So this 3d5 configuration is half-filled configuration, and we know that half-filled configuration is more stable. So the answer is already very clear. They are telling the transition metal having highest third ionization enthalpy. So third ionization enthalpy means already 2 electrons are removed, and to remove the third electron, which metal requires more energy. So here 3d5 configuration is more stable, and to remove the another electron from this 3d5 configuration, more energy is required. So the answer is clear. A is the answer. Let us check the other options also. Iron is having the configuration, core argon configuration 3d6 4s2. So in +2 oxidation state, it is having the configuration 3d6. So here 3d6 configuration is there, and by the removal of the third electron only, it is going to become 3d5 configuration. So it is half-filled configuration. So here the energy required will be very, very less, because after the removal of third electron, it will acquire stable configuration. Then going to the next one, chromium, core argon configuration 3d5 4s1. So after the removal of 2 electrons, chromium in +2 oxidation state, it will become 3d4. So here also, after the removal of the third electron, Cr3 plus will have 3d3 configuration, which is half-filled T2G3 configuration. I mean in T2G3, the half-filled T2G level configuration is more stable. So here also the removal of the third electron will give stable configuration. So this one is also easy. Then going to vanadium, argon configuration 3d3 4s2. So here after the removal of the second electron V2 plus 3d3 configuration, this 3d3 configuration we already told it is T2G3 more stable configuration. But when you compare this 3d3 and 3d5 configuration, 3d5 configuration is still more stable, half-filled configuration. So the correct answer is option A. The next question is, given below are 2 statements, one is assertion and the other one is reason. In aqueous solution, Cr2 plus is reducing. So reducing agent itself gets oxidized. So what is oxidation? Loss of electrons. So itself it loses electron. Then the other part of the assertion is while Mn3 plus is oxidizing in nature. So Mn3 plus oxidizing means it is acting as an oxidizing agent, but itself it is reduced. So itself it is reduced. What is reduction? Gain of electron. So this is the assertion. And what is the reason for that? Extra stability to half-filled electronic configuration is observed than incompletely filled electronic configuration. So we are going to see the assertion based on the electronic configuration. So first we will see the electronic configuration of chromium 3d5 4s1. Then Cr2 plus, after the removal of 2 electrons, it will become 3d4. Now they are telling it is acting as a reducing agent. So I told that reducing agent means it is itself oxidized. Oxidized means loss of electron. So after the removal of the next electron, loss of the next electron, it will become Cr3 plus. Then Cr3 plus, it will have the configuration 3d3. 3d3 we already saw in the previous question. It is half-filled T2G energy level configuration, which is more stable. So Cr2 plus will be converted to Cr3 plus easily, and it is acting as a reducing agent. So first part of the assertion is correct. Then we will compare with the Mn3 plus. So for that, let us see the electronic configuration of manganese. So the electronic configuration of manganese is 3d5 4s2. Then here they are telling Mn3 plus. So after the removal of 3 electrons, so 2 electrons from 4s orbital, 1 electron from 3d orbital, it will become 3d4. Now they are telling in that question Mn3 plus is oxidizing in nature. So I told that oxidizing in nature means itself it is reduced. And what is reduction? Gain of electron. So here Mn3 plus is going to gain electron. So the gain of electron will convert it into Mn2 plus. And what will be the configuration? So one more electron is added here. So the configuration is 3d5. So what is 3d5 configuration? It is half-filled d orbital configuration. And half-filled d orbital configuration is also more stable. So both the ions act as the given in that question. So assertion is true. And what is the reason? Extra stability of half-filled electronic configuration is observed. So in case of Cr3 plus, half-filled T2G energy level configuration, and in case of Mn2 plus, half-filled d orbital configuration, both are stable. So assertion and reason both are true, and reason is the correct explanation of the assertion. So the correct answer option is both A and R are true, and R is the correct explanation of A. Option B is correct. The next question is match list 1 with list 2. So here different species are given, and in list 2 electronic distribution is given, electronic configuration is given. So for chromium, the configuration, actual configuration is 3d5 4s1. So after the loss of 2 electrons, Cr2 plus will have the configuration. From this actual configuration, 2 electrons are lost, so it will become 3d4. Then Mn is having the configuration 3d5 4s2. Then after the removal of 1 electron, it will become 3d5 4s1. Then nickel is having the configuration 3d8 4s2. Then after the removal of 2 electrons, it will become 3d8. Then vanadium is having the configuration 3d3 4s2. Then after the removal of 1 electron, in this case, it will become 3d3 4s1. So you have to match the list 1 with the list 2. So Cr2 plus is having 3d4 configuration. So for A, option 3. Then Mn plus is having 3d5 4s1. So for option B, it is 4. Then Ni2 plus 3d8. So for option C, it is 1. Then for V plus 3d3 4s1. For option D, 2. So I will write that here. For A, it is 3. For B, it is 4. For C, it is 1. Then for D, it is 2. Now you have to check the option. For A, it is 3. So the correct option is option B. In option B only, you are having A3, then B4, C1, D2. So the correct option is option B. The next question, match list 1 with list 2. In list 1, different substances are given, and in list 2, the transition element which is present in that substance is given. You have to match that. So the first one is Ziegler-Natta catalyst. Ziegler-Natta catalyst is used for the polymerization of olefins. So it is a mixture of transition metal compound with the organoaluminium compound. So the transition metal which is present is titanium, and it is present as the compound titanium tetrachloride, and along with the organoaluminium compound, that is triethyl aluminium, AlC2H5 tris. So the first one, Ziegler-Natta catalyst, contains titanium. The next one, blood pigment. Blood pigment hemoglobin is a coordination compound of iron. So for A, the option is 4, and for B, the option is 3. Then Wilkinson catalyst. Wilkinson catalyst is used for, so I will write here, Wilkinson catalyst is used for the hydrogenation of alkenes, and the formula is RH PPH3 tris Cl. So here rhodium is present in +1 oxidation state. So chloro, tris, triphenyl phosphine, rhodium, and the oxidation state is +1. So in case of this Wilkinson catalyst, option is 1. So for C it is 1. Then vitamin B12 is a coordination compound of cobalt. So for D it is 2. So the correct answer for A4 has to come. So the only option in which A4 is there is option B. So the correct option is option B. The next question is, which of the following statements are correct about zinc, cadmium and mercury? So zinc, cadmium and mercury belong to group 12, and in this group 12 the d orbital contains 10 electrons, that is fully filled orbital configuration, even in their +2 oxidation state. For example, if you consider Zn2+, in this oxidation state also the d orbital is fully filled. So we already saw in that key concepts itself. So these group 12 elements are exception in that other transition elements. Group 12 elements are not considered as transition elements because it already has fully filled d orbital. Only partially filled d orbitals are considered as a transition element. So all the other transition elements are hard, while these group 12 transition elements are considered soft. They are soft metals. So this is the information which you should know already. So we will go to the question. So they are asking the most appropriate options. So the given options are, they exhibit high enthalpy of atomization as the d subshell is full. This one is wrong, because for exhibiting high enthalpy of atomization, more number of unpaired electron should be there. But here the d orbital is fully filled. There is no unpaired electrons. No unpaired electron is there. So this leads to weaker metallic interaction, or you can say weaker metallic bond only is formed. Weaker metallic interaction. So it is easier to convert the solid metal into gaseous ion. So the enthalpy of atomization is not high. Zinc, cadmium do not show variable oxidation state, while mercury shows +1 and +2 oxidation state. So the statement B is correct. Zinc and cadmium exist only in +2 oxidation state. They exhibit only +2 oxidation state. Hg exhibits +1 oxidation state in Hg2 2+ in this ion, in this species, and in Hg2+ in this species it exhibits +2 oxidation state. So the statement B is correct. Then we will go to the next one. Compounds of zinc, cadmium, mercury are paramagnetic, which is wrong. It is already having 3d10 configuration. I already told in +2 oxidation state also it exhibits 3d10 oxidation state only. So their compounds are having fully filled d orbital. So fully filled d orbital means there is no unpaired electrons. So that should be diamagnetic. So the statement C is wrong. Then D, zinc, cadmium, mercury are soft metals, which we already saw. So they are soft metals, while the other D block elements are hard metals. So the correct answer is B and D. So option D is correct. The next question is, which of the following electronic configuration would be associated with the highest magnetic moment? So here you have to calculate the magnetic moment. Magnetic moment formula is mu equal to root of n into n plus 2. So it is related to the number of unpaired electrons. So if the number of unpaired electrons are more, then the magnetic moment will also be the highest. So we are going to see the number of unpaired electrons. So for the first option, 3d7 is given. So if we draw the configuration like this, 1, 2, 3, 4, 5, 6, 7. So in this configuration, you are having 3 unpaired electrons. So n equal to 3. Then in option B, 3d8 configuration is given. 1, 2, 3, 4, 5, 6, 7, 8. So remaining 2 unpaired electrons are there, n equal to 2. Then here we can see that argon configuration, then 3d3. So n equal to 3. Just 3 electrons are there, no need to draw. 1, 2, 3. Then you are having 3d6 configuration. 1, 2, 3, 4, 5, 6. So the remaining 4 unpaired electrons are there. So I already told, when the unpaired electrons are more, the magnetic moment will also be the more. So in option D only you are having 4 unpaired electrons. So it will be having the highest magnetic moment.